Imagine you have just finished eating a greasy slice of pizza or working on a bicycle chain. Your hands are covered in a slick, slippery film of oil. You head to the sink and run your hands under a stream of cool, clear water. You rub and you rub, but the grease just seems to smear around, stubbornly clinging to your skin. It feels like the water is just sliding right over the top of the grease, not mixing with it at all. This is a common experience, and it reveals a fundamental truth. Water and oil on their own simply do not mix. They are like two different teams that refuse to play together, pushing each other away. Water molecules are very attracted to each other, a property we call cohesion. That cohesion creates strong surface tension. You can see it when water beads up on a waxy leaf. Oil molecules, on the other hand, are non-polar. They lack the electrical attraction water has. So, when you try to force them together, water sticks to water and pushes oil aside. That is why water alone struggles to clean oily messes. So, what makes soap so special? The secret lies in its unique molecular structure. If you could zoom in millions of times, you would see pin-shaped soap molecules. Each molecule has two distinct ends. Hydrophilic head, a water lover. The head carries an electrical charge like a tiny magnet. It is strongly attracted to water molecules. This head is what lets soap dissolve in water. Opposite end, the hydrophobic tail, water-fearing. The tail is a long hydrocarbon chain, like the stuff in oil and grease. The tail is repelled by water, but strongly attracted to oily substances. Think of the molecule as a tiny go-between, one side in water, the other in oil. This dual nature is soap's cleaning power. That two-ended design makes soap a surfactant. It reduces surface tension. Add soap to water. The water-loving heads dive in, while the oil-loving tails look for grease. They bury tails in oil, leaving heads on the surface. Water can now approach. When you introduce soap into a greasy situation, these two-ended molecules get to work. As you rub or agitate the water, the oil-loving tails hunt for droplets of grease. They burrow into the oil surface, tails inward, heads outward toward the water. As more molecules arrive, they surround the grease, forming a tiny spherical package called a micelle. A micelle is an oil droplet disguised to look like a water-friendly particle. Water sees the outward heads, not the oil inside, so the whole package can float and be carried away. This is textbook cause and effect. Cause: soap is added to greasy water. Effect: oil breaks into smaller droplets. Effect: soap molecules surround droplets to form micelles. Effect: grease is suspended in water and rinses away. It is chemistry in action. Efficient, elegant, every day. You do not need a high-tech lab to see this science in action. Start with a clear bowl, half full of plain water. Add a little oil and watch. It floats and pulls back together the moment you stop stirring. Now for the magic. 1 drop of soap. The large slick bursts apart and retreats from the point of contact. The oil breaks into countless droplets that stay suspended. Soap wraps the oil into micelles, hiding it from the water and letting it be carried off. Tip and pour. The micelles and their greasy cargo go down the drain. This is the rinse cycle in action. Proof that with help from soap, water conquers grease. Water and oil repel. Soap has a water-loving head and oil-loving tail. Soap forms micelles that trap oil and let water carry it away. That is why washing with soap and water is so effective.